So, let's talk about a scientific paper that's been out for a little while now, and yet almost nobody is talking about it. And that is just wild to me, because it represents a massive, massive leap forward in a field that quietly affects, well, all of our lives.
I mean, think about that for a second. In our age of non-stop information, 24/7 news cycles, how could something truly revolutionary just slip through the cracks? Well, it looks like that's pretty much exactly what happened here.
And hey, don't just take my word for it. This is a direct quote about the paper. And when you see what this thing can do, you'll totally get why. But to get there, first, we actually need to talk about bubbles. Lots and lots of bubbles.
I mean, these bubble simulations look incredible, right? They're just beautiful. But here's the thing. They're just a tool. The bubbles aren't the point. They're just helping us see something that's usually invisible and incredibly difficult to simulate, the complex, chaotic dance of fluid dynamics. So, what's this invisible thing the bubbles are showing us? Well, it's a concept called vorticity. And trust me, understanding vorticity is the key to why this paper is such a complete game changer.
So, vorticity, what is it? Put simply, it's all about the tiny little whirlpools inside a fluid, like water or air. It's a measure of that local spinning and rotation, and it is super important for everything from predicting the path of a hurricane to designing a more efficient airplane wing. The big problem? Simulating it is unbelievably hard. And here's why it's so punishingly difficult for computers. Every single one of those tiny whirlpools is constantly being pulled, twisted, and stretched by the flow around it. Then they break apart into even smaller whirlpools, which then do the exact same thing, on and on and on. Most computer simulators, they just can't handle it. They either lose all that critical detail and turn into a blurry mess, or sometimes they just blow up. They just stop working entirely.
Okay, so how did these researchers solve a problem that has stumped some of the smartest people in the world for years? Well, the paper itself is, super technical, but the core idea is so elegant, so clever, that we can explain it with a really simple analogy.
All right, check this out. Imagine you slice up the entire 3D world of the simulation into tiny little sugar cubes. Now, inside each of those cubes, you put a bunch of particles. Think of them like tiny little weather balloons. These balloons just drift along and ride the flow of the fluid. But here, and this is the brilliant part, each one of these little balloons has a memory. It remembers every single twist, every pull, every bit of stretching it goes through on its journey. And by remembering all that trauma, the simulation doesn't lose that crucial, fine-grained detail. So yeah, that's the difference between our simple explanation and the scientific reality. We called it sugar cubes and balloons with trauma. The paper calls it the Vortex-in-Cell method revived with a vorticity-based particle flow map formulation and an evolved flow map Hessian. You know what? I think our version is a little catchier. But what really matters is, does it actually work?
And the answer to that is a huge, resounding yes. We're not talking about a small, incremental improvement here. The results are a fundamental, game-changing leap forward in what is even possible.
Just look at that number. Let it sink in for a second. 30 times. This new method holds on to the crucial details of those tiny whirlpools, that vorticity, up to 30 times longer than the best of the best previous techniques. That is a staggering improvement to get from a single paper.
And this shows you the difference perfectly. A classic test in this field is to smash two vortex rings into each other. With the old simulators, they collide and almost immediately just smear out into nothing. But with this new method, they just keep going and going and going, holding their shape and structure for way longer than anyone thought could be simulated.
And the result of all this? We can finally create simulations that were basically impossible before, at least not at this level of detail. We can now accurately model a propeller spinning underwater, or the complex airflow over a car in a wind tunnel. These things finally look and behave the way they do in the real world. Okay, so the simulations are gorgeous and the science is amazing, but what does this actually mean for us, in the real world? Let's take a look at the incredible applications this kind of breakthrough could unlock down the road.
This is really why this all matters so much. Better fluid simulation could lead to much cleaner, more accurate predictions for extreme weather events like tornadoes and hurricanes, which could potentially save so many lives. On top of that, it could help us design more aerodynamic and, because of that, quieter and more fuel-efficient cars, planes, drones, you name it.
Now, we have to be clear, the method isn't perfect, at least not yet. It still struggles a bit with super complex shapes, and it doesn't do what's called two-way coupling. So what that means is, it can show water flowing around a boat, but it can't yet show the water pushing back on the boat.
And no big splashes just yet, so those amazing real-world applications, they might still be a paper or two away.
But even with those limitations, let's be real, a 30 times improvement in one go is absolutely phenomenal. It really makes you wonder, doesn't it? In a world that is just saturated with information and so focused on the next big headline, how many other quiet, world-changing breakthroughs just like this one are out there, just waiting to be noticed?